was what I would call the teaser. That is a simple thing. I was asked to speak very quiet. I would speak very loudly and very slowly. Now I'm going to speak a little bit more quickly and a little bit more complicated. I'll try not to speak too quickly. So we've talked then about the basic idea of linear and angular momentum. So now to try to understand, I want to think about Bessel beams, I want to think about Gaussian beams, and especially what is the relationship between Hermite Gaussian beams and Laguerre Gaussian beams, and if there's time at the end, these mysterious Ince Gaussian beams. And actually this approach gives rise to the idea of some more exotic beams, and here are some examples that I will talk about. So start with Bessel beams. So have people encountered Bessel beams before? Have you seen Bessel beams in papers or in talks? I'll show you then now, and you see it here first. So what is a Bessel beam? A Bessel beam is a cylindrical beam which is diffraction free. As it propagates through space, it doesn't change its width and it doesn't change its shape. And we can understand why by thinking about operators. So the amplitude is a little bit complicated. It's a Bessel function with this J here, a Bessel function which is the function for ripply water. If you drop a water drop, these ripples going out, they have the form of this function we call a Bessel function. And then here next to it, e to the I L times 5 times e to the I kz z. So hopefully everybody can tell me what operators this is going to be an eigenfunction of. Anybody want to help me? What operators is this an eigenfunction of? Given this here. So it's going to be a eigenfunction of angular momentum. We've already seen that angular momentum should have a factor of e to the IL5. And it's an eigenfunction of the z linear momentum operator. And what does that mean? It means that if I turn the Bessel beam a little bit, the angular momentum operator is a little turn. If I rotate it around the axis, it looks exactly the same because it looks like a cylinder. So that's why it's an eigenfunction of angular momentum. Similarly, if I push it downstream a little bit, it's a cylinder. So because it's a cylinder, then it's an eigenfunction of the linear momentum. It doesn't change, or its amplitude doesn't change, and you pick up a little phase factor, and that's what the eigenvalue tells you. So, so here's this three-dimensional intensity of a Bessel beam is cylindrical, but if you look at the phase, you have these helicoids because this e to the IL5 means you have a vortex up the axis of the beam. So this intensity, if you look at this function, these are both functions with e to the I something. I take the modulus, I just get 1. So the only variation in intensity comes from this radial behaviour, and it's not an eigenfunction of radius, it's an eigenfunction of angle, and it's eigenfunction of z if you think in terms of linear, in terms of cylindrical coordinates. So what is a Bessel beam? It turns out a Bessel beam is an eigenfunction of the Laplacian. It satisfies the Helmholtz equation with eigenvalue k squared. It's an eigenfunction of angular momentum. It carries orbital angular momentum and has a vortex on the axis of the beam. And it's an eigenfunction of pz. It doesn't change as it propagates. So now we get to a more complicated example. You might think that Gaussian beams are the most familiar beams, and they are, but actually they're quite complicated. And one of the hints about how they're complicated is there's all of this stuff to do with Laguerre Gaussians and Hermite Gaussians that you might not understand why that should come up. So what is a Gaussian beam? Well, of course, if I have a laser, what is it? It's really a confocal resonator. I have a confocal resonator. I have two parabolic mirrors here, and if I think of the ray picture, the rays bounce back and forward, but they always are inside this shape here. and if you actually plot what a Gaussian beam would look like inside a cavity, the wave has exactly the same shape as this family of rays. Now, this is actually, from a quantum mechanical viewpoint, what we would call a two-dimensional harmonic oscillator. Why should that be? Because, for example, if I use an ABCD matrix system, as these rays bounce back and forward, as they propagate through space, they just have a regular Hamiltonian of free propagation. Regular Hamiltonian of free propagation is p squared. But then when they reflect off the mirrors are parabolic. And if the mirror is parabolic, that acts like a potential. Parabolic, it means it's a quadratic potential. So the effective Hamiltonian for the rays is actually p squared, px squared plus py squared, and x squared plus y squared. Here's the square of momentum in 2 dimensions. Here's the square of position. And this is like the Hamiltonian of the wave in this plane here, the focal plane of the cavity. So some of it comes from the free space between the mirrors, and some of it comes from the fact we have parabolic mirrors. Now what about Hermite and Laguerre Gaussian beams? So we have to think about this cavity, or what's going on in this cavity, to be able to understand Hermite and Laguerre Gaussian beams. And what I said was, it's related to a two-dimensional harmonic oscillator. And I hope that you, in your lectures, have studied a little bit about harmonic oscillators in classical physics. Yes. Is that correct? I'm glad to hear it. Next week, when I return back to Bristol, I will be lecturing our new first-year undergraduates in classical mechanics, and harmonic oscillator is the second example. So, my favourite example of harmonic oscillator, so long as the angle is small, is just a pendulum, but a pendulum that is free to move in 2 dimensions. So, what does a pendulum do in 2 dimensions? One, it could swing back and forth, like a one-dimensional pendulum. But another thing it can do is it can rotate around. Now, one of the things that's interesting, I think, about the rotating around a circle is the swing goes back and forward. There's no overall sense of linear momentum. It's going this way and it's going this way. But if I have the rotating motion has a single fixed direction. So it's a little bit like we were talking about before, where you think maybe something is actually like a standing wave because it's going forwards and backwards, and maybe other things are not standing, they're travelling. And if you look, the first hint that this may be the right thing to think about is a Hermite Gaussian looks a bit like a standing wave back and forward, yet a Laguerre Gaussian doesn't have any fringes, it actually is going in a single azimuthal direction. So, in England we have a saying, when we say something, it has advantages and it has disadvantages. And we say, it's like swings and roundabouts. You know, if you go to a children's play area, you sometimes see some swings and you sometimes see some roundabouts. And so I like to think, actually, thinking about two-dimensional harmonic oscillators is swings and roundabouts. Sometimes it's easy, and sometimes it's not easy. So if you come across two-dimensional harmonic oscillators, you all study optics. So what's the simplest example in optics you can think of a two-dimensional harmonic oscillator? I would think it's the polarization of light. Because if you think about it, light, it goes back and forward like this if it's linearly polarized, or it goes round in a circle, or in general, it can do, I didn't talk about it, it can go round like this, which is like elliptically polarized. So actually, if I want to talk about the two-dimensional harmonic oscillator, I should think about the Poincare sphere. But we're not talking about the Poincare sphere for polarization, we're just thinking of it as a representation of a classical two-dimensional harmonic oscillator. So here's a picture of the Poincare sphere. So on the equator are all the linear polarizations with different angles, and at the pole, North Pole is right-handed circular, and the south pole is left-hand circular. And it turns out this is their very natural way of thinking about polarization. It's certainly what we're supposed to be using. And so it's nice if you're doing experiments, because the Stokes parameters, the x, y, and z axes in the sphere, can just be taken as the difference of two measurements of intensity behind a polarizer. But also, so that's if you're an experimentalist. If you're a theorist, you like them because they're like expectation values in quantum mechanics of Pauli spin matrices. So it's clearly the right thing we should be doing if the experimentalist wants to do it and the theorist wants to be doing it. And in fact, this shows up in many other areas of physics. For example, in quantum mechanics of spin, you may have encountered this notion of the Bloch sphere, which is the space of directions of a quantum spin. And it actually has very much similar to a Poincare sphere for the polarization of light. Now that's one way of thinking about polarization, but it's not the only way. And I remember when I first learnt about polarization, I was a bit confused.